Hello, hello.
Check, check. Yes, and maybe if you could plug this in, I could try the
So the thing is, I don't know how to use one of these, so I think it should be fine, right? Just, I don't know any weird, the Windows laptop. It's been a while since I.
Okay, no, you just have to.
Sure. Yeah, that I can, yeah. I'm not a Luddite, I just Mac challenged. Okay. Can I take this?
Yes.
Okay, good. Okay.
Start.
Sure.
Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Gautam Dasarathy. He will be speaking on learning where to look, reliable certificates under Scarce ground truth. Professor Gautam Dasarathy is an associate professor at the School of Electrical, Computer and Energy Engineering at Arizona State University, USA. He is also an Amazon scholar in Amazon Last Mile Sciences. His research focuses on statistical machine learning, information processing, and network system. He received his PhD from the University of Wisconsin-Madison and held postdoctoral positions at the Carnegie Mellon University and Rice University. He received the NSF Career Award in 2021 and the Distinguished Alumnus Award from his alma mater, VIT University, India in 2022. Over to you, Professor.
Okay. Thank you for the kind introduction and for the invitation. I'm going to talk to you about this problem that's been annoying me, but as good problems do. And it's a sort of new framework for thinking about a very old problem, which is common in statistics, which is two-sample testing. So if I were to be, okay, this has to happen, right? Why does this not go forward? Yeah, so there you go. So if I were to give this a little bit less lofty title, it'll be label efficient two-sample testing. So I'll tell you more about what this means, but this is a sort of new twist on this sort of classical problem of two-sample testing from statistics. The motivation for all of this is what one might like to call AI-driven science or AI for science. And oftentimes now the typical protocol, if you are an AI for science scientist, is to come up with some new features that you think are going to be interesting. If you can't come up with features, you just throw a machine learning model to try to discover features. And then use that to enable some capability that was traditionally very hard to do, right? So here's an example. Maybe you invent a new, in collaboration with people who are experts, you invent a new digital test for detecting whether a person is, let's say, prone to Alzheimer's, right? So this is a very important problem, especially in several countries around the world. We are getting slightly more aging populations, so people are very worried about this. And let's say that the sort of ground truth, which is not quite ground truth, but still at least something that's been validated over several years, is a PET scan, which measures something called the buildup of something called amyloid. Okay, so it's a particular modality. We'll not worry about all the underlying details, but several of these things are pretty well known and easy to find online. Right? So you, the machine learning scientist, or now I'm contractually obligated to call this AI, you, the AI scientist, has to go and, let's say you come up with this new tool and your hope is to be able to replace the stuff that is done by traditional bioimaging people with your new tool, right? And of course, the promise is that this new tool is way cheaper to do, right? It's more scalable. So if it's like, let's say you ask someone to write a paragraph on an iPad and then just observe how they write, that's way cheaper to do. You can do it remotely. You can do it for several people, as opposed to this, which is super hard to do, right? You have to bring them in. You have to run an expensive PET scan. Right, so the question, if you have invented this tool, and maybe if you want to get funding for this, or if you want to prove this as a valuable alternative, is this any good, right? Does this digital test do a good job of predicting whether someone has Alzheimer's? Or is this a good stand-in for this sort of amyloid buildup, right? So typically, the way one would go about this in science is you take a bunch of people, you call this a population, you take a bunch of people, and then you divide them into two groups that you care about. So in this case, it's people with high amyloid buildup and people with low amyloid buildup, right? So you bring all of these people, you do these tests, you split it into two groups, and then for each of these groups, you kind of compute this new test that you have proposed. So I'm just calling this test results. So you ask them all to write one paragraph in the iPad, and then you want to decide whether the distribution between people with high amyloid and people with low amyloid, if the distributions look very similar or look very different, right? So is the picture more like that, or is the picture more like this, right? So if both of these point clouds of iPad test results look very similar, then let's say there's more homogeneity in these populations, then maybe you cannot use this iPad test, which is cheap and easy, to actually tell apart these two groups, right? On the other hand, if it does look reasonably different, then you can use this to tell things apart. And this is our premise. So this is what we do in order to decide whether this new test that you have proposed is good or not. Okay? This has a name, by the way. Yeah.
So this assumes that the PET scan is infallible.
That's right. So I'm only trying to replicate something, the PET scan at this point. Yeah. So of course, if the PET scan is itself bad, I mean, the statement that you would make is this new proposed test is a good stand-in for the PET scan, right? And then there's a future, I mean, down the line, which is the PET scan a good stand-in for actual Alzheimer's prognosis or something? That's also an interesting scientific question. But for now, we are trying to replicate the results of this expensive to validate thing. Right?
Isn't it also important that not only are the distributions separated like this,
Yeah.
the individuals who fall into one group should be the same individuals who fall into that group under my new test.
Very good. Yeah. So I've suppressed a bunch of details. So quick question, technical people. If questions in the audience, can the Zoom folks hear it? Is there mics in the? Oh no, that's okay. Yeah, I'll just repeat the question. Yeah, I'll just repeat the question. So the question was a very good question, which is if let's say people who wear black shirts always have high amyloid, and people who wear red shirts always have low amyloid. So if there's somehow you have this inherent bias in how you split the data, then maybe your test is just picking that split, right? So you have to somehow be fair in randomizing between these two groups. And yeah, so in this step, I've hidden a bunch of things, but there is careful experiment design. So you have to sample in a way that similarly featured people are in both of these groups, and then can you still tell the difference and stuff. So you want to disambiguate the effect of just the amyloid on the prognosis of Alzheimer's, right? So that's, you have to do this a little carefully. In fact, we consider this a little bit more seriously later on, and I can talk about that later.
What I mean is that just look at the distribution.
Yeah.
If you just look at the distribution of the new digital test results,
Yeah.
it might be separating people into two nice groups.
Right.
But the individuals in these two groups may be a very different split of the population compared to the split of high amyloid group and the low amyloid group.
Yeah.
Right? So let's say there were 50 individuals there, 50 individuals here,
Right.
and there are 50 blue dots here and 50 red dots. They're nicely separated, but
Right.
the 50 people in the blue dots are completely different from the 50 people who are in the low amyloid group.
Right. No, so actually, yeah. So this is even more in the basis of this problem. I know who are the high amyloid individuals, and I'm going to color all of them blue. And then I know who are the low amyloid individuals, and I'm going to color them red. So I'm only testing if the red point cloud is overlapping the blue point cloud too much or not.
Okay.
So here I already know the separation.
Right.
So I thought you were asking something even more subtle, which is you have to be careful in experiment design so that you're not picking up some latent factor. But I think you're okay with this, that I'm assuming there are no, or at least we have a sort of control for these latent factors. But modulo that, there's a good question. I have to be careful. We already know who is blue, who's red, and I will only call it a win if the clusters that the iPad test discovers respects the blue-red split. Right? If it's some other cluster, then it's still not a good idea.
Yeah. Thanks.
Cool. Great. Any other questions? Please keep stopping me, and I'll be happy to take questions. Especially, I have front-loaded motivation and problem setup because I think the problem setup is quite interesting. The solution we can even dive into detail offline. Okay. So this is a classical two-sample testing problem. In fact, if you can state this mathematically as follows. If I give you two samples, so by the way, if you're from an ECE background, which several of you are, when I talk about samples, I mean in the statistical sense, a group of individuals. In ECE, we talk about samples as one draw from a distribution, right? So I mean, if you have two sets of draws from two different distributions, let's say P and Q, where P, for instance, could be the high amyloid and Q could be the low amyloid. Your goal is to test between these two hypotheses, which is H naught, P is equal to Q, that is these distributions are indistinguishable, or P is different from Q, right? So this is the question that we want to answer, and the question is, can your sort of iPad test, your new test, be able to tell apart these two things, right? So this is the problem setup. By the way, two-sample testing is everywhere. So for instance, let's say, this is a slightly more related example. Everybody nowadays, yeah. Yeah, so I'll call that features or data points. So the question here is, what's the typical dimension of the samples? I won't deal with this explicitly now, but let's say we will think about it as a d-dimensional vector for now. And all of the results will scale with that d, right? And it does, for instance, this is a very interesting question because it really, the dimensionality of the vectors makes the problem much harder, right? If it's super high dimensional, then we know this from, let's say, I mean, you're teaching a class on concentration inequality. So if you're doing high dimensional statistics, we know that several points in high dimensions look equally far away, and telling apart distances is hard. But a whole field is devoted to that kind of stuff, like sort of high dimensional non-parametric statistical testing. So for now, I'm going to assume it's D, and I'll let all of it scale with D. I just won't make it worse than what those people know how to do. Okay, so that's my guarantee to you. Cool. So several people now have these smartwatches, and they keep rolling out new features. Apparently now it can tell you if you have an arrhythmia. It can tell you some other things, the heart rate monitor on your watch. Now, how do you validate this? Well, it's you get this sort of data, and you have people who are, let's say, have some kind of cardiac problem, and people who don't have this cardiac problem. You have these measurements from both of these groups. You want to check if these measurements overlap or not, right? So it's a two-sample test. This is how you validate something like this. So, similarly, if you're doing some sort of fraud intervention, like let's say if you're a bank and you want to do fraud intervention, you want to check between whether the transaction is fraudulent or not. This is often a two-sample test. And more recently, people are getting super interested in this so-called model monitoring or ML ops kind of problems, where let's say you train a model, you deploy it in the wild, and so you want to make sure that the data, the distribution that this model was trained in is similar to the distribution it's being deployed in. And the idea is that you want to do a test between how the distributions look. So people think about this as distributional testing, but also you can kind of phrase a two-sample testing problem here, right? So this problem comes up everywhere. And this goes back in some sense to the core of how we started doing science, right? There's this really beautiful book called A Lady Tasting Tea. It's a really nice book that walks you through the history of statistics and things like hypothesis testing. Does anybody know what this person, Gossett and Guinness, has to do with any of this stuff? You don't have to tell me the answer, but if you know, can you raise hands? Okay, at least one of you. Okay, so this person's name is William Gossett, and he used to work in the Guinness company, and apparently they didn't let him publish. So he figured out a way to do a really clean, well-validated test between, I don't know, like a beer that is good versus beer that is bad, or let's say a vat that is good versus vat that is bad. This is a statistical problem at its heart. So he published under a pseudonym, and the pseudonym was Student. So if you have used something called the Student's t-test, which is all over the place, Student is Gossett, right? And this, like this is a very biased and sort of very sparse history. Wald Wolfowitz, they in like the 1940s, they proposed this sort of runs test, which is more non-parametric, because if you have a model for how the data comes, then you can test for differences using things like the mean or the variance and things like that. If you don't have a model, you need to come up with something that's non-parametric, and these folks did this kind of really well. It's very famous. Then Friedman and Rafsky. I just found out that Rafsky has a company now, but essentially, Friedman and Rafsky in the late 1970s, they did this really sort of high-dimensional variation of this Wald-Wolfowitz runs test, and it's very beautiful. So even though it's somewhat tangentially related to this talk, I'll dive into more about what Friedman and Rafsky did. And the modern era, like Aditya asked, is essentially about filling up all of this into high dimensions, right? Because you now have data points that are, let's say, millions and even like billions of dimension. How do you do reliable and valid two-sample testing in these high-dimensional settings? Okay, so this sort of is a really old problem, and it has kind of come hand in hand with how science has progressed, because anytime you want to make a scientific statement, you're essentially doing a hypothesis test, right? Okay, so we can get into the philosophy of this, but to some, let's say, some conceptions of how science works is essentially hypothesis testing. Okay, cool. So again, I'll sort of set up the two-sample testing problem. You have these two samples, or two sort of sets of IID draws from two distributions P and Q. Well, these two are allowed to be the same, right? That's what we are testing. So two potentially different distributions. And you want to do the following test. And usually how you do this is you compute a statistic from the data, so something that summarizes these two data, or this pair of samples. And then you reject H naught. So this is how you do proper hypothesis testing. You don't ever say H naught is, so you don't ever say H1 is true. You reject H naught if this statistic is too extreme in some sense, right? So you set a threshold, and then you compare the statistic to the threshold, and then you reject H naught. Right, so from a signal processing background, we see this in things like estimation and detection theory, where you want to do some kind of hypothesis test to figure out if, I don't know, like if a signal was sent or not, right? So this comes up all over the place. And you might have seen figures like this. We could presume that H naught has, under H naught, this test statistic has some distribution like this, and under H1, it has some distribution like this. And this threshold is where we make the decision, right, to satisfy some trade-off. And these things are pretty well known. I won't get into too many details, but there's so-called type 1 error. So I like the EE term for this. I forgot to put this in. but this is called the probability of false alarm, right? So essentially, H0 is true, but then you reject it, which means you think that there is some signal there, right? So this is called the probability of false alarm. And then there's also type 2 error, which is the other way around, where H1 is true, but then you fail to reject H0, right? So, so this is essentially, all of these things are sort of basic stuff. These are, let's say, performance metrics for understanding hypothesis testing. And the reason why I'm putting this up is because we respect all of that while coming up with this new twist, like I said. So the classical, so I wanted to walk you through one way that we do two-sample testing in practice. So this is, the Friedman-Rafsky test comes up still all over the place. And it's a really nice test that it scales readily to high dimensions, except you have to do a lot more theory to make sure it works. And so here's how one might do this, right? So imagine that you have two cases, and these two cases are, these red and blue dots are super overlapping versus these two are not overlapping, okay? Oh, I did some slide translation between my laptop to this, and we're losing some captions. But it's okay, I think we can make this out. So there are these two cases. What the Friedman-Rafsky test asks you to do is pretty wild. Okay, what it says is you construct a minimum spanning tree on the graph whose nodes are these things, right? So the idea is that there is a distance metric on the space, right? This is just the Euclidean distance metric, and you plot all of these points in space, and you can think that there's a complete graph that connects all of these things. So every pair of nodes is connected by an edge, and the length of that edge is essentially the Euclidean distance between those 2 points. And you drop edges such that you're left with a tree, and the remaining tree is the tree whose sum of total weights is the minimum, right? So this is called the minimum spanning tree. Classical problem in computer science, it comes up all over the place. And Friedman and Rafsky said, first construct the minimum spanning tree, right? And when I first read this, already it blew my mind. Like, so on the one hand, we started with somewhat an abstract problem, right? You have these points in d-dimensional space, and there's some underlying distribution, and you want to check if these two distributions are the same or not. And then your proposal is to construct this very, very geometric or even combinatorial object. And I was like, where is this going? Right? I was in suspense when I started reading the story. So you construct this minimum spanning tree, and their test statistic, so you remember I told you like you need a summary of this data points to figure out whether the distributions are same or not. Their test statistic is what we would call cut edges. So these are the edges that connect a red dot to a blue dot, okay? So these are, in this figure, it's a little hard to see, but these dashed lines are the so-called cut edges. It connects a blue dot to a red dot. And intuitively now it starts making sense, which is if more blue dots are connected to red dots, this means these distributions are a little bit more interleaved. So the higher the number of cut edges are, the less likely the distributions are to be far apart. Right, so in this example, in this whole chunk, there are no dashed lines. In this whole chunk, there are no dashed lines. And only when these two meet, there are some dashed lines. Right, so they propose this as a test, right? I mean, this, anybody can say whatever you want, but really you also want guarantees, right? You want to show that something like this is actually a good idea. That's where all the magic is. So I wish there was some text that worked, but okay. So, but at least like we have a theorem. Okay, at least this part showed up. Okay, so the theorem is that the normalized cut edge count R, we'll call this R, under H0 is asymptotically normal. Right? This is already kind of wild. So they're saying that they can show a distribution for the normalized cut edge count, and it is normal with mean and variance that you have analytical expressions for. Right? It only depends on dimension of the space, and it depends on the number of points and stuff, and we can actually write this down. Right? So what this means is I can tell you if these two distributions P and Q are the same, I can precisely tell you what the bell-shaped curve of this test statistic looks like, which is the number of cut edges in this thing, right? And why is that useful? Well, because I know what it looks like typically. If something deviates from it significantly, then I can construct a test based on that, right? I can do so-called p-value, all of those things. In fact, you can construct what's called a permutation test to get somehow really precise hypothesis test that works all the time. Right, so this was Friedman and Rafsky's sort of main contribution that and statisticians go through this sort of evolution where they first try to characterize what it looks like in the null case, so the null distribution. And once you understand the null distribution, which is typically because of central limit theorem like things is normal or normal-ish, then you know the distribution under the null, so that then you can say, okay, if something else happens, at least I can rule out the null, right? So, and the probability that I'm wrong, you can compute based on the bell-shaped curve, and you know how to do this. So this was a pretty big deal. It's a big result from the late 70s. And then Henze and Penrose, who showed that the FR test is actually consistent. And what that means is, notice that this null, this result tells you nothing about if the distributions are actually separate, right? So you would like to also know if there is some signal here, which is, let's say the distributions are separate, then the test statistic has to capture that, right? Like the test statistic should be non-zero, or it should be some value that is interesting. And what they showed is that the normalized cut edge count, which is, I'm normalizing R by, so let's say this makes it seem like R itself is normalized, but maybe I should have normalized this. But modulo all of those details, if you normalize properly, which is with the total number of points, then this actually converges somewhat intuitively pleasingly to a measure of divergence between P and Q. So this quantity is called an F divergence, and this F divergence is some measure, like let's say if you've seen KL divergence and all those things, F divergence is in that family. It's a measure of divergence between these two distributions. So if P and Q are not the same, then this is sort of by definition non-zero, and this quantity converges to 1 minus the distance between these two distributions. Okay, so this is the Friedman-Rafsky test.
Sorry, what are M and N here?
So this is the total number of points that you had in the blue clouds and M cloud, the red clouds essentially.
And they are different. Yeah, correct.
So it can be different. I mean, usually I would just think about this as, so the question was, what are M and N? So M and N are essentially, M plus N is the total number of points you have. So in some sense, this sort of edge itself is symmetric modulo the counts. So you just want to make sure that the counts are normalized. Any other questions? So
It's R over M plus N.
R over M plus N.
Not R over M.
No, yeah. So this is a keynote bug. It was not able to, it's like R over, big over M plus N. Yeah. Cool, okay? So this is, I should have just called it normalized. So if you normalize this properly, then you get this measure. So in particular, the takeaway message here is that if P and Q are not the same, then the KL divergence between P and Q, so the F divergence between P and Q is some value, and this quantity converges to that. If P and Q are the same, then this actually converges to 1 minus 0, so it converges to this constant C, right? So otherwise it converges to something slightly less than C, and this tells you how far apart things are. And if you have done things like concentration inequalities and all of these modern finite sample data analysis, this should ring some alarm bells. Like you can now possibly do some finite sample guarantees, where you can say, okay, I have an epsilon gap between 1 minus df and 1, so how many samples do I need in order to actually provably show that these two things are different? So all of these things can be done, except those things require sort of distributional assumptions on P and Q, otherwise you cannot get weights and things like that. So if you don't want that, you need to at least show something like consistency. Okay, that is, you have if there's some signal, eventually I'll be able to recover that signal. So this is a particular F divergence. Yeah, the details are in the paper. Some very specifically chosen concave function that gives you this. Yeah. Cool. So now actually we'll come to the thing that motivates me, which is there's a catch. In all of these examples I gave you, I sort of strategically picked those examples, is that the group membership is often hard to determine, okay? And what I mean by that is, remember we have this is the setup that we started with. You invent a new digital test for Alzheimer's, and there's this sort of PET scan, which is the ground truth. So like Chandra said, we are only trying to replicate this PET scan results. So there's some ground truth. In fact, we are thinking that there's something that the doctors agree is high amyloid and low amyloid based on the PET scan, and that itself, that's the ground truth. Right? That's the two classes that we're trying to distinguish. And So we have this is the setup that we have, and our goal is to validate whether this is a good idea for telling apart these two things, right? So this is where I propose a two-sample test. The catch is that it's super expensive to actually do the PET scan. Right? It's super easy to have a bunch of people go and write a paragraph on their iPad. You can just ask them to download this app and write a paragraph. This population of digital test results is very cheap to get. And then you do some kind of sampling. And for the samples, if you want to reveal all their amyloid amounts so that you know which population these two things belong to, that's super hard to do. Right? It's very expensive. You have to take them into the lab and then spend a bunch of money, technician salary, all of those things to get these results, and then get it scored by a person who knows what they're doing. All of that costs money, right? In fact, this group revelation is what we're going to start targeting. This happens in several other examples. So for instance, in this sort of digital health thing, the same problem. Digital health data is easy to get, especially if you already rolled out watches. You just add a new app to this watch, and you can get a bunch of data. But then you have to do lab tests to figure out whether actually this person has arrhythmia or not, right? Similarly, this happens in model monitoring, financial fraud detection. And right now I was talking to Sid, who's in CSA, and in several problems in fairness, this happens as well. So let's say you roll out a model, and you want to check if this is fair with respect to some protected group. You know what the model is doing, but you don't know the protected features of this population. So if you want to pay someone to go and collect these protected features, it either costs you something like either money or some kind of, let's say, lack of trust. Like someone comes and asks you, which on this protected features are you at? Maybe you kind of feel bad about this company, right? So maybe you want to not reveal that too much, and there's a cost to revealing which group people are in. Right, so this motivates the problem that I'm talking about, which is how can you do two-sample testing when things are actually expensive to reveal which group they are in, right? So it kind of flips the two-sample testing problem on its head. So what we propose to do is a sort of modification of this two-sample test, where instead of exhaustively or sampling all of these people to do the PET scans on, we're going to do what I'll call active selection, right? And so this has connections to active learning, except it's a somewhat dual version of active learning. So you do some sort of active selection to carefully pick a bunch of people for whom you would like to do this sort of revelatory PET scan, okay? And here, to reveal the amyloid amount by the PET scans, like I said, it's very expensive. Instead, what you do is you only do this for a limited number of people. Right? Because you're using this sort of active querying, you can reveal this only for a few people. And then again, you split it into this high amyloid and low amyloid group. And with this, the question is, can you do a two-sample test? Okay. Any questions about this, about the setup? So the hope would be, let's say you roll out some ML model, and you want to figure out if it does differently for a protected group. You don't ask the protected variable for everybody you're rolling this model out to, or a large population. You only ask this for strategically chosen people. Right? And this, if you have seen things like active learning, is exactly the kind of thing that people like to think about. Yeah.
So you look at the outcomes of the cheap test and then decide whom to test next.
Yeah.
Who run the expensive test on.
That's right.
And also it is one shot. That is, you can run the cheap test, and then you decide on whom to run the expensive test on.
Right.
You run that, and now you have to make your decision on whether the cheap test is good or bad. You cannot select a small number of people to run the expensive test on, look at those outcomes, and then go back and select another small group, etc. That is not allowed.
So great question. So I guess you did on the mic, so hopefully people heard that. Yes, so the way that I'm setting up right now, it's all of those things that you said are correct. So the first thing is that you first see the outcome of this cheap test. So essentially, you can imagine that, so I'm essentially assuming that this is freely available, right? You can look at a person and then look at their iPad results or whatever. But really what will happen is someone will build this thing, roll it out. There's some sort of experiment enrollment step that should happen if you're actually doing a medical test. But modulo that, everybody gets this result, and then you record the results, and I'm going to charge you nothing. So this is free. So everybody, for this whole population, you have this digital test. And then you look at the output, and you get one shot to decide who to sample to bring into the lab, right? So you bring them all into the lab. you make a determination whether they are in the red group or the blue group, and then you have to do this two-sample test. But we do adapt it to the sequential version. So essentially, there are various reasons why you would like to adapt to the sequential version, because sometimes it's just easy to tell that these two things are different, right? Somehow, let's say if everybody you sampled is just like way off the charts in the amyloid level, then the test is one particular way, and then way below in the other way, then you should stop the test early. So you would like to do early stopping. So that's one reason why you would like to do sequentially. The other reason is you want to be effective, right? Like, so maybe you can get more signal if you sequentially query which ones to sample. So I'll talk a little bit about that. I wanted to spend more time on sort of motivating this problem, but I'll go into it a little bit. So there's a paper that kind of covers that.
I'm a bit confused about what is the actual objective.
Yeah.
When you say a digital test, it is a per person measurement.
Yeah.
It's not a hypothesis test.
No. So sorry. So maybe I should not have used a digital test, but here, let's say it's an easy to acquire feature. So it's a digital feature or something. In digital health, sometimes they call this digital test because you ask them to perform a test. Especially for Alzheimer's, it's like a.
So let's say you have a very limited number of really expensive tests.
Yeah.
That's like a label, like gold standard.
That's right, and that you have a budget for a limited amount. Yeah.
And you have an unlimited budget for the cheap label.
Cheap label. Yeah.
A noisy label for every.
That's right. Right.
And finally, after the strategic choice of costly labels, you observe the costly labels for those particular individuals.
For the choice, yeah.
For the choice. And then finally, what is the metric of
Yeah.
your
So
system?
the metric is.
Or what are you required to output finally?
Yeah. So the metric is. So let's say that all of these people exist in some space, right? So the space is abstract. Let's say they're just people in space or something. Then you get to observe nothing interesting about them except for the outcome of the PET scan. So the classical two-sample test is you observe the outcome of the PET scan, and you have to tell if some feature of the person that you've observed is different or not with respect to this outcome, right? So do red and blue people look different with respect to some features that you measure? So in this problem, like especially if you're adapting it to digital health, the feature that I care about is the outcome of this digital test. So there's some features that we care about. And so if you featureize with respect to this space, is there a distributional difference between people with high amyloid and low amyloid? But you don't want to reveal the amyloid content for everybody because that's expensive. Yeah, so your goal ultimately is just a two-sample test with respect to high amyloid and low amyloid. So this part, once you phrase the statistical problem, this part is a distraction. Okay, so this is just for motivation. The features just exist, and that's what allows you to, let's say, parameterize the space and throw it in some test. Like to even deal with this, you need some features, right?
I guess so the P distribution in your two-sample test is the distribution of your cheap test results for the gold standard positive group.
Exactly.
And the Q is the distribution of samples of your cheap test for the negative guys. Okay.
And if your featureization or the digital test outcomes do not respect this high and low amyloid group partition, then you cannot do the two-sample test. But if they do, then you can, right? That's the point. Yeah, exactly. Great question. Cool. Any other questions? Cool. So the idea is you carefully select the features that you care about. So for everybody, you have features or the outcome of this digital test, and then you query them and then do this sort of two-sample test. So I think this is a new two-sample testing problem. I'm ready to change my mind, but we have been kind of trying to push this a little bit. So the new two-sample testing problem, where you can phrase it like this. We can talk mathematically in a second, but like we just discussed, there's a large population of sample features and a very limited labeling, or to be more precise, or let's say a little bit more pedantic, is by labeling the group membership associating budget, right? So you want to ascertain which these people are, and your goal is to develop this sort of label-efficient two-sample test, okay? And the goal, of course, always is to whether these two samples are drawn from the same distribution or not. And one way to think about this is, you have this cloud of points. I changed out the color because red and blue here. I don't want to. There's no correlation between these colors and these colors. But essentially, there are two groups, and if you sample some groups, if you sample a subset of these people and then reveal their PET scans, and let's say orange is high and green is low, and if they look very different, maybe you want to tell that these two things are separate. Right? That's the whole game. Okay, cool. So one thing that I like I come from an EE background. So one nice way to think about this is through a generative model. And here's a sort of interesting generative model for this, which is almost entirely equivalent to what we've been talking about. And imagine that nature selects some z at every round. Nature selects this Bernoulli random variable z. And when z is 1, you draw a sample from this p distribution, and when z is 0, you draw a sample from this q distribution. And what you get to see is this pair s comma z, right? So instead of thinking about it as colored dots, imagine you see a feature and then a color, right? Whether it's 1 or 0. So then the two-sample testing problem essentially is an independence test, right? Because what you're trying to ascertain is whether this s random variable, which is what feature there is that independent of z, which is which distribution this thing was picked from. If p and q are the same, notice that the conditional distributions are the same and these two things are not independent. So it's the other way around, right? If p and q are same, then s and z are just independent. So it doesn't matter what z was, s is going to be what it is. So you can conclude that these two things are independent. On the other hand, if p and q, if these conditional distributions are different, then you will see that s and z are not independent, right? So this really becomes an independence test. In fact, for the sequential version, we use this very intimately, right? In fact, we construct a test statistic sequentially that is a mutual information estimator. And this is a very nice, there's a lot of literature on how to do that and how to do that effectively. Okay. So without further ado, I'm going to tell you my algorithm. I feel like I've just been building up. And this algorithm is like dirty simple, right? That's the main reason. I feel like a lot of the interesting stuff happens sort of problem setup and then the theory. But the algorithm itself is sort of very simple, and it's also very natural, right? So your goal is to test whether two things are different. What we say is first look at some subset of data. So that you have some budget, shrink that budget significantly. So take a small portion of that budget and just randomly select a bunch of features and reveal their samples. So you first go out and get some data. I guess maybe I answered Chandra's question a little bit. Slightly imprecisely. There's almost two stages, if you will. So first, you randomly select a set of features and reveal their labels. And then what you do is you train a classifier, you train a binary classifier using this training set to obtain a conditional distribution of this z given s. Right? So can you decide which color you should be based on just the feature that you observe? Right, this is a classification problem, so you can train a classifier to do this. And most classifiers, actually well-calibrated classifiers, actually allow you to output the conditional probability distribution, right? Not just the labels, but also the probability distribution. So you train a classifier, and then what you do is, using the rest of your label budget, query the labels corresponding to high values of p hat z equals 0 given s and p hat z equals 1 given s. Right, so we call this bimodal query. And the idea is that you look at points where given, for this classifier, you look at points where given this feature, this is the highest chance of being a high amyloid person and then the highest chance of being a low amyloid person, right? You only query those people. So don't query anybody else, only query those people, okay? So if you're familiar with active learning or things like sort of the active sequential learning, this is the exact opposite of what active learning people do, right? So active learning, the idea is to query at the boundary. In some sense, you want to query where it's super hard to tell whether this person is 0 or 1, right? You query, usually, they call this information gain, and they call this sort of querying as you want to minimize you want to query at the margin, right? But this is the opposite. You want to query where you are almost certain, right? And or you think you're most certain. So that then you can do a statistical test to figure out how that looks. Okay, And then after you do this, so this is sort of, so Chandra, it's like a kind of two phases. You do train a classifier, and then you do this sort of next phase. And this, now you collect a bunch of labels, right? So you throw away everyone else. You collect a bunch of labels whose you have this gold standard PET scan. And then you use that to do the 2-sample test. So for instance, you can do the FR test. So our paper is based on the FR test, but we show in an appendix how this generalizes to several other tests, like the Chen test and all of those things. Okay, so any questions about this? So this is the 3-line description of the algorithm. So Dheeraj. Yeah.
If I have very, very few samples of one kind.
Yeah.
So that when I run this, when I run the stage 1 test,
Yeah.
I might never touch anyone from that region, right?
Yep.
So
Yes, absolutely. So when we're looking at theory, so the question was, if you missed the first part in Zoom, the first question is, are there any assumptions, or do you need any assumptions on like, I don't know, like the distribution of classes, right? Totally. In fact, yeah, when you're doing theory, you have to do all of these things, where you have to say there's a good chance that you might miss all the high amyloid people because they're super sparse in the population, right? We like sort of following trend with classical statistics. We only have asymptotic results, where what we show is that the fraction of queries that we require compared to what you would require classically is vanishingly small. So it's asymptotic, so eventually you will hit that, right? So if you want finite sample results, totally, you need to do that. And in fact, you need to make assumptions about something about the distribution, essentially, tails of the distribution, so that you're making sure you can sample enough, but also the F divergence is well separated that you can hit and stuff. That's one thing that we need to do. The second thing we need to do is make sure, how well does the classifier do is also important here, right? If your classifier is bad, then you're going to do a bad test. So there are some assumptions we make on the calibration consistency of the classifier. And so in asymptotics, this is okay. And in some sense, this is a hard problem in statistics where for type 1 error, you can get it somewhat easily, but even that is usually in asymptotics. And for type 2, essentially consistency or power, you can only say that if you make some assumptions. If you don't make assumptions, then anyway people only expect these sort of asymptotic consistency results. And for all of those, all of the sort of calibration consistency and all of those things work. Right? So yeah, so that's a good question. So if you're looking at the large data limit, then you will eventually hit enough for this to work. Any other questions? You had a question.
Your first step involves, you have some budget of costly labels.
Yeah.
You're just randomly picking these labels.
Right.
Is it possible to squeeze something more out of it by being adaptive?
Yes.
Okay.
So this is kind of, I answered Chandra's question, which is also slightly related to this. But here, as soon as we wrote this paper, we asked this question, which is why are we doing this sort of two-phase thing where you first sample randomly and then you do this? Instead, we have a way to do this entirely sequentially. So you just do one by one, and you build this sequential statistic. You prove that it's a martingale, and then you can show all of these things. But yeah, so totally. In fact, yeah, even that is a little conservative, so I'm sure there is better ways to do this. In fact, here's an example where you should be able to do better. Imagine that you know some topology of the space, and you have a suspicion, as scientists do, right? Like we have a suspicion that just by the topology of the space, we can tell where these samples lie. Then you should use that also, right? Like so somehow space-directed sampling. So we don't do any of that. We can do sequential though. So potentially we could early stop so you don't completely do this random sampling. Great. Cool. So this is a actual simulation, but there are more results in papers that you can look at. So if we do this, imagine that these are the two classes. They're slightly different. So I had a little bit more detail, but it was too much, so I just kind of hid it. But I can tell you numerically how different they are offline, right? So it's a two-dimensional thing, point clouds where the two distributions are slightly different, and these are just for simulation's sake, they're just Gaussians, but none of the theory or method requires that, right? So they're slightly different, and these green dots on top of these are essentially what the random sampling phase does, right? So you first do a bunch of random samples, And then what you do is you train a classifier, and once you train a classifier, you query at the mode, and this is what that part looks like, right? So I just ran the algorithm and plotted which was queried when, and this looks like this, right? So what has happened is that once these points as labels were revealed, the classifier kind of figured out that here is the most likely region where 0 is, and here is the most likely region where 1 is, right? Or red is and blue is. And then your second phase just samples there. So it gives your two-sample test the maximum chance to tell these two things apart, right? And that's what this thing looks like. So now the two distributions of red and blue are going to look very different, right? This is what we're going to leverage in our method. So I could have essentially done this talk with this one slide, and then we could all gone home, right? So this is what the method does, and this is why it is a, let's say, label-efficient two-sample test. Okay. So what does this really do? I don't know if you're from a slightly theoretical bent, maybe that picture doesn't doesn't satisfy your curiosity. And I have a sort of a sketch of a theorem statement here. And then I'm happy to chat about all the details, either through questions or offline. But if you assume an appropriate classifier, okay, huge chunk under the carpet, if you assume an appropriate classifier, which is, like you can define this formally calibration consistent and stuff, then under H1, this is under the null hypothesis, the distribution of the features S selected by our method, which we call bimodal query, converges to some distribution P star S. Okay, so this is the main sort of content of all of this work. And what is this distribution? It's the distribution that makes the Friedman-Rafsky statistic, so the FR test statistic, maximally powered, right, in some very formal sense. That is, if we can define a notion of what maximally powered means, which is it has the best chance of telling those two things apart, given a label budget. And it turns out that P star S is the limit of this query procedure and this query procedure's sampling distribution converges to that. So just to remind you, S is the feature that we are calling, right? So once I hid the X and Y, S is the feature. So this is the digital test or whatever. And what we are trying to characterize here is what is the distribution of features you have selected after our method? What does that look like? What that looks like is it looks like the one that Friedman-Rafsky test succeeds as well as possible, right? So this is the main theorem. So the proof idea is that we have to show some a structural result about this Friedman-Rafsky test. And so what we show is that the Friedman-Rafsky test converges to some function of P of S and this conditional distributions. And then what we show is if you, this thing is minimized by exactly this P star S distribution. Right? So that's the basic architecture of the proof. All of these require some analysis, but this can be done. Okay. Are there any questions? So this is the basic idea where we are this sort of sequential. This active procedure gets you maximal separation with respect to the sampling distribution. Okay. So the other thing we show, which is should be shown, is that under H naught, which is, let's say these two distributions are the same, then it turns out actually it doesn't matter what you do because anyway it's just random, right? So it doesn't matter if you hallucinate a classifier, the resulting points are still from this sort of same distribution P and Q, so you should still be able to do a two-sample test. Provided you have not oversampled and stuff, so modulo some of those details, you can actually show that this thing controls the type 1 error. So it turns out that the previous theorem looked more impressive, but actually that turned out to be the more straightforward part of this whole thing. Showing that the type 1 error is first statistically the most important. When you're writing a science paper, you have to report a p-value, though people are trying to change that, but you have to report a p-value which says, what's the likelihood that this thing that you observed, this phenomenon that you observed, just happened by random chance? So if you're constantly claiming like scientific discoveries, but your p-value is super high, that means that there's a very high chance that this thing just happened by random, right? So you want to be able to control the type 1 error, which is related to the p-value, okay? So we show this result in this paper, okay? So a token sort of experimental result. I'm happy to walk through some other things that we ran offline, but essentially for this there's this ADNI data set, and in this data set it turns out that there are sort of 5 cognition-based scores, and we can actually do much better than just randomly sampling using our method, right? So there's sort of bimodal query type 2 error as a function of the proportion of queries that we actually do does significantly better than if you just do random sampling. And by the way, this uncertainty is because we were curious what happens if you do traditional active learning where you try to sample based on the uncertainty of points. It turns out, not very surprisingly, it doesn't do as well because you're constantly muddying the two sample test with points that are kind of ambiguous, right? So you don't want to do that. You want to kind of let them separate out. Cool? So I think we're good on time. I have one more slide that is going to answer all the professors here are laser sharp. They're like, okay, what's the next paper we can write? So at least I can tell you the next papers we wrote after this, and then we can, you can tell me what other papers we can write on top of this, right? So the first question, which came up a couple of times, is why are we doing this in this sort of constrained way where you first pre-collect a bunch of samples, a small number of samples, and then pre-collect a huge number of samples, and then you're stuck with this. So naturally, the question is, can you do this sequentially, right? Like go out, sample if 3 people, get their results, and then see who you need to sample and so on. Yeah. Yeah. Yeah, I can repeat the question now. Yeah. So the question was, you need to have sort of, you need to decide how you allocate your budget to the random sampling phase and let's say the active sampling phase. I did not comment on that, but we have answers for this thing. So it turns out that any reasonable fraction would actually do well, but the open question is how to optimize that fraction, right? And that will require assumptions on how well the classifier is calibrated and stuff. So if your classifier is fantastic, then you can get away with a lot fewer random samples. But if a classifier is a little bit more noisy, then you need more samples. So I think there's interesting theory and practice to be done here where you understand this trade-off, right? Between how good your classifier is and how much you can bootstrap it to do the 2-sample test. A great question. But what we made our peace with is if you don't want to assume anything about what classifier people are using, then at least like if you do a sensible fraction, let's say alpha 1 minus alpha, where alpha is non-vanishing with respect to certain parameters, then you can get meaningful results. Okay, so this thing is, I won't go through all the details, but essentially we can do this sequentially. All the buzzwords are all highlighted, but you can go check this out. Essentially, the idea is that you will maintain a running test statistic where you kind of like sequentially build this test statistic up, and our method produces anytime valid p-values. Right? This is the problem with sequential tests. You need to make sure that the p-values or your type 1 error guarantees are always holding because you're getting more and more data. It turns out there are sort of standard ways to do this, and we can do this stuff. And the most crucial thing, especially from a practitioner's point of view, is that it enables early stopping, right? So if you want to stop the procedure because you're sure that either there's no chance these two distributions are different, or these distributions are clearly different, then you can stop soon. Right? And it turns out that another thing that's super nice is that the test statistic that we construct converges to the mutual information between the feature distribution and the group distribution, like the Z random variable I told you about, which is nice because it's an independence test. It clearly naturally translates into a power statement, right, or consistency statement. So okay, in practice, it turns out that you get similar power with much fewer queried verifications. By the way, power is just the reverse of the type 2 error, right? So essentially, power just means you're doing well, okay, under H1. So we also have this sort of thing where there's another natural question, which is imagine that there's a cohort of people who respond very well to an intervention, and there's another cohort of people that don't, and your 2-sample test is deciding whether there's a difference between these two cohorts, like significant difference between these two cohorts. The other question is, how do you identify the cohort, right? If you're doing a clinical trial, you not only want to figure out if your drug is efficacious or not, like nobody's going to be like, I'm going to deploy my drug at random at this population and then decide if this drug is effective or not between the control and people who have been intervened on. I also simultaneously want to figure out what is the subgroup of this population where this drug is the most effective. Right? So it turns out that if you don't do that, if you allow the responding cohort to be drowned out by a sea of people for whom this drug doesn't work, then your two-sample test is going to be useless. But if you somehow adaptively figure out what the subgroup is, then actually you can get a significant effect, right? So in clinical tests, this is what they do in like the stage 2, stage 3, and all of those things. So essentially, we also adapted this to so-called enrichment or cohort finding. And it turned out we needed to do like this version called matched pair experiment design, but I'll be happy to talk about this offline in the interest of time. But essentially, it uses the same kind of philosophy and principles and the same human power to do this. There was a group of us that did all of this. Speaking of which, I should thank Weijia, who's like the main driving force behind all of this. He's on the faculty job market, but I don't know if he'll apply. I don't know where he's applying. But Prad, Karthi, they're all collaborators, a combination of IBM, Mayo, and Visar, who's my colleague at ASU. Okay. So thanks to folks. I'll leave up a takeaway slide, and then I can take more questions. But here are the takeaways if you're just waking up. But all of you have been super engaged, but thank you for that. The takeaway slide is, I think this is a new take on hypothesis testing. It's not going to be relevant to all problems, but I think for a significant fraction of problems where it is difficult to tell apart this group membership, this is a new twist on this problem. And we did this sort of label-efficient two-sample test, and we proposed this algorithm that gives you, that is an asymptotically valid, it's asymptotically consistent, and provably better than passive sampling. What I couldn't go into detail, which I just flashed one slide about, is this sort of sequential version, which clearly people are interested in that, so I should have started with that, but maybe next time. We adapt this sort of walled-like sequential probability ratio test, like SPRT, to create this sort of anytime valid sequential test, so that you can do this thing sequentially, and also this cohort enrichment and matched pair stuff. So if you want to learn, this is a little hard to see, but if you want to learn more about this, we had this thing called an advanced tutorial at the Winter Sim conference. It's a tutorial that sort of summarizes a line of work. And so that's a nice place to sort of get both a high-level picture, but also deep dives that are across several papers. So I'll leave this here, and I'll take any more questions if there are.
Thank you, Professor, for accepting our request and delivering an interesting talk. Are there more questions from the audience?
By doing this, the expensive test, are you not introducing a bias in the expensive test? And if we are to do the other way, just to make a kind of much more random sampling on the expensive test, and then you have an unlimited budget on the inexpensive test, would it perform better?
So that's a great question. So that's two parts to that question. So let me take the first part on, which is actually the thing that made us the most nervous throughout this whole process, right? So this flies in the face of what good statistical testing is supposed to be, right? So what is good statistical testing supposed to be? It's supposed to be blind to as many variables as possible, and then by being blind, and we go through a lot of lengths to make sure this is the case, right? This is why we do randomized controlled trials. We do double-blind experiments. The reason is we don't want to be biased by what we see, right? And it's supposed to be randomly sampled or randomly assigned, this control and treatment groups, so that we disambiguate a bunch of things. And then when we measure a signal, that signal is real, right? That's what good statistical testing is supposed to do. We are advocating for something exactly the opposite. What we're saying is you bias yourself with respect to this, with this classifier, and then you try to do this test, right? So in fact, you could imagine the following happening. Imagine that P and Q are actually the same, but you have taken a small amount of data, and the small amount of data, somehow it's like telling you that P and Q look very different because like the classifier is wrong or whatever. It tells you you're super extreme along this axis. So you think that these two things are different. This could totally happen, right? So the guard that we have against something like this happening is the guarantees on how well the classifier performs with respect to the total distribution, essentially. So if the classifier is bad, then we are hosed. But if the classifier is reasonable, then we can actually make sure that we can control the bias that we get with respect to the amount of budget that we have. So that's the first answer to your question. I don't know if that satisfies you, but essentially you can control the amount of bias you inject into this process by controlling the fraction of points that you use to build the classifier. At some point, if you're saying, hey, I don't trust the classifier at all, then you just let the budget saturate the whole thing, like the whole space of points, and then you just do a classical 2-sample test. So what we show is that whenever possible, we can turn that down a little bit, and whatever we leave on the table translates directly into power savings or power gain, essentially. So that's the answer to one question. So I don't know if that satisfied you. The second question is, why don't we do it the other way around, which is, why don't you randomly sample the expensive stuff and then get the cheap stuff more adaptively? But so I think that in my conception, the cheap stuff is truly cheap. You just have as much as you want of it. So if you just randomly sample the expensive stuff, then you're just comparing to random sampling, which we show does much worse than the adaptive sampling. But that's an interesting modality, and maybe we should chat about this more. But if I do this in my naive conception of what I think you're saying, we tried that, and it just is equivalent to doing just randomly picking a bunch of people to label, and that just has less power than doing this sort of in this intelligent way. Yeah, it is a little counterintuitive. Okay.
You mentioned that here, when you do the active sampling, your goal is to select points at the extremes of the distribution, not really at the boundaries.
Yeah.
Can you elaborate on that a bit? Because you want to really see that your classifier is as good as the ground truth-based classifier, right? So if you're wrong on a lot of the people at the boundaries,
Yeah.
but then yes, in some extreme cases you're able to classify correctly, that's not really good enough, right?
That's a great intuition to have. So typically, this is why I kept saying this point again. In active learning, the goal is to make sure that we do well at the boundaries. Let's say you want to build a classifier, let's say between people who have high amyloid buildup and low amyloid buildup. So I've changed the problem. You have to look at some features and build a classifier. Now, now my measure of error is going to be how well you do on the population, right? So if I give you a random person, if I throw this person through your classifier, are you correctly going to detect what their amyloid level is? If you do this, if you make a bunch of errors along the boundary, then you're going to perform very poorly, right? Because a lot of people you're going to misclassify, and then in the extremes you get it right, but who cares, right? But you're going to make a bunch of errors. But we have the opposite goal. So our goal is not to build a good classifier. Our goal is to say, if there exists a signal, that is, if there exists some sort of difference between these two distributions, the place where that difference is most likely to show up is at the extremes. So if the distribution is slightly different, then in one extreme that distribution is going to be really different, and the other extreme, the other distribution is going to be really different. So as long as the classifier does well with respect to the extremes, then we can actually do a 2-sample test to tell if these two distributions are different or not. This classifier is going to really perform poorly at the boundary. But if at all there exists any bit of signal, that signal is going to appear at the edges. So this is actually the crux. So, this is what we proved when we proved that theorem, where we showed actually this distribution that this converges to is the minimizer of the test statistic with respect to the Friedman-Rafsky test. So, and you can actually set up, so you can, I could have presented this whole thing in a boring way where I just say, I'm going to write down this optimization problem, which is minimize the Friedman-Rafsky test statistic with respect to some sampling distribution. And it turns out the correct sampling distribution is sampling the posterior means of this sort of classifier. Yeah, so this is good intuition, because it kind of is, that's why I call this somehow dual of active learning, where you're kind of polarizing yourself a little bit. Yeah, you want to evaluate whether this classifier is picking any real signal or not. Yes. And if the classifier is picking even a little bit of real signal, it has the most likelihood of doing that in the posterior means, in the extremes. And so also the counterfactual is interesting. Let's say there's no real signal, so this classifier is hopefully only randomly classifying things. Then even in what the classifier thinks is the extremes, the labels are going to be random, right? And then your two sample test will be able to tell that apart. So as long as we impedance match these two effects properly, then we should be able to do a proper valid two-sample test. Yeah. Okay.
Thank you again.
All right. Thank you. Yeah.
Thanks very much for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there.